Welcome to this explainer. Let's just jump right in, because I am incredibly excited to uncover the hidden physics behind the food we eat every single day. You know, if you've ever looked at a perfectly clear glass of apple juice, or maybe a perfectly smooth carton of milk, and wondered how they get it so incredibly consistent, well, you are in the exact right place.
Okay, let's start with this totally counterintuitive idea. Food factories are not just cooking food. They are constantly separating materials. It completely flips how we normally think about food processing, right? Because it turns out industrial food production is actually way less about cooking and far, far more about separation.
And looking at this massive modern factory brilliantly illustrates the sheer scale of the engineering required to actually pull this off. They rely heavily on mechanical separation, using these highly engineered continuous systems to process things like milk, juice, and flour at an absolutely massive scale. And the crazy part? They do it entirely without altering the fundamental chemical makeup of the food. So, here's our roadmap for today. We'll start with the big picture, then cover the 4 pillars of separation, dive into gravitational sedimentation, compare good versus bad sedimentation, and finally, look at centrifugal separations.
All right, section 1, the big picture. Why exactly do manufacturers rely on mechanical separation instead of heat or chemicals?
Well, the crucial point here is that by exploiting pure physical differences between materials, stuff like size and density, factories can achieve separation without any phase changes and completely without chemical additives. This is a huge deal. It protects heat-sensitive products, maintains extremely strict regulatory safety standards, and, as a massive bonus, saves immense amounts of energy and cost, all while remaining completely scalable for enormous volumes.
Moving on to Section 2, the 4 pillars of separation.
Now, what's really fascinating here is how we can categorize all of this massive industrial machinery into just 4 distinct physical mechanisms. We've got sedimentation, where natural gravity allows denser particles to settle. Then we have centrifugal methods, which basically amplify that gravity. After that is filtration, using a porous medium. And finally, sieving, which relies on a physical mesh barrier to intercept particles by size.
And whether we're using direct restraining forces, like that physical mesh barrier in sieving and filtration, or indirect gravitational forces in a giant settling tank, the ultimate goal across all 4 of these groups is always exactly the same. We are trying to establish relative motion between the fluid and the particles.
Let's dig deeper. Section 3. Gravitational sedimentation, which is basically the slow and natural route. The physics of this natural settling process are governed by a really beautiful equation known as Stokes' law. It tells us that settling velocity is dictated by particle diameter, particle density, and fluid viscosity. So, in everyday terms, this means that larger, denser particles suspended in low viscosity or thinner fluids are going to fall and settle the absolute fastest.
But hey, it's really important to note that gravity doesn't always pull things down. Sometimes it actually causes less dense particles to float upward. This is a process known as creaming, which is exactly what happens when less dense fat globules in whole milk naturally rise to the surface instead of sinking to the bottom.
Now, if we need to artificially speed up this natural settling process in a factory setting, we can introduce things called flocculants. These chemical additives promote particle aggregation. Essentially, they force tiny particles to clump together into much larger, heavier forms that fall a lot faster.
When a uniform suspension is left to settle under gravity, it doesn't just happen randomly. Over time, it organizes into 3 very well-defined zones. You get a clear liquid zone at the very top, a uniform suspension zone lingering in the middle, and a dense sediment or compaction zone at the bottom. And understanding this specific behavior is absolutely critical for engineers who design industrial continuous clarifiers.
You can see this developing over time here. It brilliantly illustrates those 3 accumulation zones. Watch how the perfectly clear liquid grows at the top, while the increasingly dense sediment rapidly accumulates down at the base of the vessel. Which brings us to Section 4, good versus bad sedimentation.
Depending on what a factory is actually trying to produce, this settling process can either be the ultimate goal or a complete disaster. Sedimentation is fantastic for clarification and recovery, like, say, if you want perfectly clear wine or you need to recover valuable yeast from a broth. But on the flip side, it represents terrible product instability and quality degradation if you're trying to sell a beverage that requires a perfectly uniform texture.
Seeing unwanted sedimentation in action is honestly striking. On the left, we have chocolate milk without stabilizers. The cocoa and fat particles have quickly separated under gravity, stratified, and essentially ruined the product for commercial sale. No one wants to drink that. But on the right, stabilizers have been added to coat the particles, completely preventing sedimentation and maintaining a beautiful uniform suspension.
All right, our final stop, Section 5, Centrifugal Separations. So, the inherent problem with natural gravity is that, while it's completely free, it is exceptionally slow. It takes hours for cream to separate from whole milk naturally, and in a modern industrial setting, waiting hours is just a massive bottleneck for dairy factories that rely on high-throughput, continuous processing. To solve this, engineers turn to extreme machinery. By using an ultracentrifuge spinning at up to 100,000 revolutions per minute, we can actually achieve radial separation forces exceeding 500,000 times standard gravity. Let that sink in for a second. By amplifying radial acceleration with these absolute behemoths of industrial machines, factories can transform a density-based settling process that normally takes hours under natural gravity into an operation that is completed in mere seconds. It's a literal game changer. Internally, they utilize different rotor designs for very specific needs. A fixed-angle rotor provides a short path to create fast, tight pellets. A swinging bucket rotor actually swings out horizontally during operation, which is perfect for creating really sharp density bands. And a vertical rotor gives the absolute shortest sedimentation path for rapid band formation. The math behind this is honestly beautiful. Centrifugal acceleration scales with the square of the angular velocity. What that means in practical terms is that simply doubling the rotational speed of the centrifuge literally quadruples the physical separating power. 4 times the power just from doubling the speed. It's an incredible multiplier effect. Which brings us to the end of our explainer. I want to leave you with a bit of a challenge. The next time you grab a perfectly clear juice or a uniformly smooth chocolate milk from your fridge, I want you to look at it through the lens of physics. Ask yourself, what invisible, massive physical forces had to be amplified just to put that specific product on the shelf? Thank you so much for engaging with this breakdown of the hidden world of manufacturing. Keep learning, and we'll see you next time.